You may be familiar with the Lorenz attractor, a classic example of deterministic chaos, where tiny differences in initial conditions grow exponentially over time. For decades, mathematicians searched for a true three-winged Lorenz-type attractor. It doesn't exist. What exists instead is what you're seeing here. But this system, called omega-3, reveals something deeper. What you're watching is not chaos appearing all at once. It's structure slowly losing its ability to keep track of itself. Chaos emerges only when information loss escapes structural constraints. At every stage, information is folded forward and cannot be recovered. But at first, the system has strong symmetry. That symmetry acts like a bookkeeping system. Even though information is lost, the system still knows where it went. For a long time, the trajectory locks into a clean geometric skeleton. It repeats, cycles, and revisits the same finite set of vertices again and again. Complexity grows, but it's a symbolic complexity. Long patterns form, but there's no randomness yet. Now watch what happens as the symmetry is gradually weakened. At first, nothing dramatic happens. The shape deforms, but it holds together. The system is still leaking information, but the leakage is trackable. Structure survives. Then we hit a tipping point. Suddenly, the vertex count explodes. The orbit stops, returning to the same location. The geometry smears. Predictability collapses, not because the system became more nonlinear, but because the leakage can no longer be followed. This is where randomness appears. There's an interesting detail here. If you start the animation directly at b equals 0.73, the vertex count drops to 1. It's not because the system truly has a single vertex. What's happening is that the trajectory falls into a narrow attractor well at one vertex, and the counting algorithm locks into it. If instead you approach b equals 0.73 gradually, the full 12 vertex structure appears. This matters because it shows what you see depends on the information that you carry forward. The system hasn't changed, the tracking has. And that brings us to the key idea. Irreversibility alone does not create chaos. Irreversibility with symmetry produces structure. Chaos emerges only when symmetry can no longer constrain the leakage. The implication is broader than this system. In physics, computation, and even number theory, complexity does not automatically mean randomness. Often randomness occurs only at the final stage, when structure can no longer keep track of what's being lost. Chaos isn't the default. It's what remains after structure runs out of ways to remember.